to know that there is a record of these presentations. Good. Well, I try to and sharing mode. Oops. Yes. So then I'm looking for Mr. Grote. Is he still already available? I see. Perfect. Hello. So very good. So the first presentation will be given by Fabian Grote. Fabian holds a PhD in physics and started his career at Covestro in 2016. Today, Mr. Grote is segment manager for LED lighting in Europe, Middle East, and Africa. And Mr. Grote will give us an insight in the new demands and applications for polymer optics in general lighting and automotive lighting from a material supplier's perspective. So the stage is yours.
Thanks for the kind introduction. Let me quickly see that I get this on full screen. I lost my mouse and it's not on full screen. Now, is it on full screen on your side?
Yes, perfectly.
Yes, so thanks for the kind introduction. And I'm really looking forward that we are having this event now, finally today. I want to talk about new demands and applications for polymer optics in general and automotive lighting. And it's my intention of this call to inspire you. I will not give each and every single detail of the technology that I will show, but I want to spark some ideas on your side, and then happy in the Q&A session or maybe after the event to follow up on these topics. Yeah, something that is very hard to do these days, sitting alone in the home office. So I hope I get across some inspiring visions of what polymers can do in the future. Very briefly, so I work for Covestro, a global polymer supplier headquartered in Leverkusen. It's having 3 different businesses. One of the businesses is our polycarbonates business, and that's what I'm going to talk about most of the time today. So let's take a first look into the agenda, and that will look a little bit different to an agenda that you will normally see. And working in polycarbonates now for a few years, I and also my colleagues, we have realized that polycarbonate becomes an enabling material across the whole electromagnetic spectrum. If you look across frequencies, if you look across wavelengths, you will find applications that are empowered by polycarbonate. And that spans across different sections, communicating, sensing, and lighting, and then across different applications. In communication, these are some topics like 5G, for example, IoT, and so to speak. In sensing applications, you see very dominant applications like radar, LiDAR applications, which are dominant in automotive industries, autonomous driving, etc. Works with sensor transparent polycarbonate, for example. And then that is where I will my focus today is the lighting area. And I will touch on interior lighting trends for mobility. And I will exclude, due to time reason, what happens on the exterior of a car. And then go into E&A applications and look in different applications here and what are trends there from a material perspective. However, we will see throughout the talk that we will see conversions of different industries, and that maybe even 5G sensing and so on also becomes important in lighting. First of all, very briefly, if you don't know what polycarbonate is, it's an engineering plastic, so thermoplastic material. And basically, it has 5 key properties that you need to understand for this talk. It is transparent, so you can use it for optics and optical applications. I think the most one of the key criteria is here. And then it is heat resistant, flame retardant, and impact resistant. So it's a product that is heavily used in technically demanding applications. And last but not least, it has an excellent colorability. So whenever it comes to design, aesthetics, polycarbonate is a very good material to choose from. So with that said, let me jump into the first application I would like to touch on, and that is called 24/7 seamless mobility. And I think I don't need to talk a lot about autonomous cars and how the experience will change, presumably in the future. However, light will play a key role here. Yeah? The concept you see here was a concept we have developed for KFET 2019. It's a real concept, not an animation, that is standing in our technical center in Leverkusen now. And I want to highlight two aspects here which are relevant in the sense of lighting. Yeah? On the left-hand side here, you can see, I would like to draw your attention to the flooring. Yeah? So you see an illuminated floor, which you would probably have never seen in a car before. And that is made out of natural material. So you have actually a natural floor ceiling, which is illuminated. Yeah? And you could even envision that to be made out of wood. So something that is fairly unique for lighting purposes. Yeah? Or on the right-hand side, you see light integration into seat areas. So it looks like leather. However, leather can't be light through, but eventually something like that will become possible. And these are now real examples. So you look onto the top side, it's a natural material, it's marble and slate on the left side, it's a natural wood finish on the middle side, and a vegan leather and in-skin technology from our company on the right-hand side, which really feels and touches like leather. On the backhand side, you have transparent polycarbonate directly injection molded onto the metal, onto the natural material, and then it is light through. So you can have stunning. I hope it comes through the short videos how you can see light animation actually going through these natural materials. And that is something that will really open up new possibilities for designers in the future. However, how to make that possible is not so straightforward. If you look on the right-hand side on the top image, you see a standard polycarbonate injection molded onto a stone veneer layer. And you see how the material starts to bend, which is not an issue normally for polycarbonate, but this natural material has its a tendency to bend. And that can be overcome when utilizing glass fibers. This is what you see on the second image on the right from the top. However, when you use glass fiber material, typically you have the issue of poor optical quality. So it's a tendency to turn yellow, very hazy. And that's what you see on the third image from the top. So polycarbonate with glass fiber filled. However, we were able to overcome this issue to have a glass fiber filled product, which is extremely tough with a tensile modulus, very comparable to standard glass fiber filled grades. However, it still offers you the transparency you need for these natural surfaces to be integrated into applications. With huge benefits in terms of weight and functional integration. So that's one of the very first trends we are seeing, especially in the interior of mobility. Jumping ahead, I would take a brief look into this trends in general lighting and then walk a bit through different applications here. First of all, I think, long story short, LED bulbs is a story that everyone has in his house today. It's a market that has peaked, presumably in 2019. And when something like that happens, typically you see new innovations coming up. And the innovation cycle where we are in at the moment, which I would call a second wave of LED lighting, is LED luminaires. So you have LEDs, chip-on-board technologies. I'm not talking anything new here, but that is what is happening in the market currently. And I want to show one example here of what is important nowadays from material perspective to participate in this trend, and what kind of properties we need to take further into what I will call a third wave of lighting. And that is a wave of convergence of different industries. So light being adopted by very classical E&E applications, maybe even by healthcare applications, or even light taking on new applications like sensing or something like that. Let me quickly start with what we're seeing in the market currently and what are success factors from a material perspective. The key differentiator for luminaire manufacturers, which are our customers, is a term called luminaire efficacy, so the number lumen per watt. And that is the case because in technical luminaires, the customers of our customers typically buy, I don't know, 500 to 1,000 luminaires equipping whole parking lots. And then it really matters how energy efficient they are. And one example here is a diffusion product that we have developed based on theoretical studies and simulation, is a product called DQ5122. And just by replacing the cap of that luminaire. It's a tri-proof luminaire, 1.5 meters long, 15 centimeters wide. We could improve the lumen output of that luminaire by 6%. And that's something the industry is striving for. And that should just stand here and as an example of the whole portfolio that we're developing on lighting products. The key purpose or the key idea behind our products is increasing this term lumen, the term lumen output. Here on an example on a diffusion product, but it can also take into transparent products and so on. So now looking a first glimpse into what happens when different industries come together. And that is a concept that we have developed with an external design agency that really utilizes the full potential of polycarbonate technology, and it combines this with sustainable design. First of all, what you see is a security light with a proximity sensor that can detect you and indicate that it has to detect you, and then can pull off deterrent LED lights if you approach too close. So a lighting element in here. However, these things will become smart in the future, or are already becoming smarter, and integration like brand logos, IR sensors, camera optics, audio input, output. By the way, audio, smart speakers, polycarbonate is the material of choice here. And adoption of wireless connectivity, may it be Wi-Fi or may it be even more advanced applications like 5G. So why I'm explaining that concept here, it's basically three aspects are important: efficiency, connectivity, and sustainability. And in terms of efficiency, it's using less parts and using processes like 2K, film insert moldings to actually manufacture these devices with as little components as possible, as efficient as possible. These things should be connected in the future. And when we talk about connectivity, a key element here is to be transparent for certain wavelengths. And this is reflects back to the agenda that I have shown. I'm looking into frequencies in the 5G area and the Wi-Fi area. The materials need to be censored or wavelengths transparent in these areas. And then, for example, also the cooling area, like the Macrolon TC, so that is the back molding you see here. So you can even handle the thermal management components of such lighting elements, while still accounting for good Wi-Fi and signal transparency, which is probably not possible with aluminum. And then, obviously, the most important part of the design concept was to show possibilities how to ensure a sustainable design. If you look through the concept here, you see that only the electronics components are not made out of polycarbonate. It's all other elements are made up from our portfolio. Transparent, films, reflective whites, TC, and even the mountings, it's all made out of polycarbonate, which makes it significantly more easy to recycle such a product at the end of life. So this design for sustainability is a key aspect on the material perspective, but also the concept here omits any kind of glues, of screws. You have some breakaway features to take the electronics out. So again, further big trend beyond the pure optical properties is to think about the whole design of such a luminaire. Second example from that conversion of industries is EV charging and lighting. A booming industry these days with electric vehicle coming on stream these days. We have looked with students from Umeå Institute of Design, a design university in the north part of Sweden, into new design concepts for such EV charging points. And we had 15 students working on these concepts, each developing an individual concept. And we realized very quickly that light plays a key role here in terms of human-machine interface, so to speak. So one purpose light can fulfill is if you drive through the city, light can tell you whether a charging station is occupied, whether it is free, or maybe whether it's booked or reserved by a person already. Or light can use a daytime, nighttime design, or it can indicate the charging level. So you have vast opportunities here to communicate via light. However, in such kind of applications, you see very different set of properties that you typically see for lighting applications. So you have a very demanding safety aspect. So the flame retardancy goes up to a UL 94 level of 5 VA, maybe 5 V0. So very tough flame retardant requirements. You need to be impact resistant to be vandalism proof. And on the third aspect, which is a key, aesthetics. So you want this light integration, you need transparent products fulfilling that, good surface finishing, and also designs and operators, they want to brand these charge points. So that's obviously also where light will play a key part in the future. And in completely new products, like a product, the LED 5902 FR that we have developed and launched recently, is combines these optical, really superb optical functions with excellent flame retardant properties. And in my last example, I would touch on a project that we have done with some of the people here on the call that I will disclose shortly. It's edge lighting, freeform and freeformed surfaces. Yeah, again, enabling new design opportunities. We have developed 3 concepts. They are 30 centimeters high, 15 centimeters in wide, a polycarbonate light guide where the light is coupled onto the edge and then coupled out on the surface. And I want to show 2 of these concepts to quickly explain how they work. You can see here, if you look onto the middle image, on the long edges on the right and on the left, we have LEDs coupling into a 3 millimeter thick light guide that is microstructures on the has microstructures on the inside. And then if you turn either to the left or to the right, you can see how the intensity of that light beam actually decreases. So having a low glare design just realized by microstructuring. And the second design here, we couple into the other edge, so to speak, into the curved edge, which on the top left image is now facing towards you. And when you start turning that towards the back towards the right, and you go through the top images and then through the bottom images, you clearly see how the intensity increases. Yeah? So you can really realize, even in the asymmetric light distribution case here, really targeted light distributions. So on the right side, the image quickly depicts how that looks like. You have an LED on the edge with microstructures, which have a certain size, a certain geometry, a certain spacing, and then can couple out light in a very calculated and predicted way. And what's fascinating me about that project is that there's lots of different competences that you need to bring to one table. So obviously optical materials, that's a competence of polycarbonate, of Covestro here, or other players. So you need innovative tool and mold manufacturing, where we have the company Hofmann assisting us. Simulation of free-formed microstructures, optical light guide. So that simulation aspect, the company Polyscale was doing that. So how do I get a certain lighting geometry? How can I calculate that back into the microstructure geometry that I need in my light guide? Yeah, how does that work? Very complicated part and very essential. And then fourth, you need someone who can actually fabricate that and bring the microstructures into an injection mold. And that's where we had the Fraunhofer IPT coming into play. So lots of different, very unique set of skills. However, that is not able if you're lacking one of these skills on the table. And that's something very unique. Let me conclude on my last slide and take the 4 takeaways from these different examples that I have shown. And the first takeaway is that natural materials, yet lightweight and functional, are on the horizon. So technically that's feasible and something that really opens up design opportunities looking into the future. Secondly, which might sound a bit odd, but optical material properties will remain important. Very heavily that was driven on transparent grades in the past. However, we do see that also coming into what we call compounded grades. So these DQ diffusion products, for example, where you have a certain set of additives inside, your plastic material into your polycarbonate. That gives you that lighting geometry of a diffusion material. But also when it comes to, for example, sensing transparent products. I haven't touched on that here. LiDAR is such a topic in automotive interior, where you need, even in the non-visible area, so in the IR areas, where you need specifications for your products, which specify how much LiDAR actually is out. What is the light output of your product specified? Very interesting area, and definitely a trend from a material perspective. Certainly, very heavily driven from that conversion of different industries. Flame retardants will likely gain important in optical applications. And last but not least, design for sustainability aspects. How do I design luminous or any kind of other applications in such a way that it can be recycled at end of life, and that can be some kind of processes or engineering tweaks that you can do, and also that concept of monomaterial design, that you use less or fewer amount of different materials, you avoid kind of glues, etc., but then become really a monomaterial design body. So with that said, I would like to leave some minutes for questions, and happy if you want to contact me after the call. You have my contact information here, but I'm also happy now to take the questions live here.
Well, thank you very much, Mr. Grote. So I heard that there are some people having problems with raising the hand with the Zoom. So in this case, just go ahead and you can ask your question. So I would again ask, are there any questions to Mr. Grote?
I would like to ask a question, if I may. You just showed the transparency values, which are something around 80, 85, 80, 83 or something like that. Is there any attempt to get that better?
So you may refer to one of the slides that I have shown in context with FR, maybe one of this slide here. So with polycarbonate, the theoretical limit you can achieve is slightly over 90, it's like a 19.x%. Yeah? And we offer products which are very close to that. However, here the sense is that you want to have a certain property, this flame retardance, to come up to a very high and very demanding level. And matching a transparency of 89% or higher with that flame retardance is, to my knowledge, the best in the market that you can actually find these days. So please don't start to compare that maybe to PMMA with optics, but PMMA would, it's different material.
I was curious.
Yeah, it's very close already to the theoretical limit that you can achieve. Jump back.
There's one question in the chat. Oh. Could you please comment on the autoluminescence of your material?
Good question. Question is in which kind of wavelengths maybe is he referring to? Maybe also depending on additives used in color recipes, etc. Maybe difficult to answer straight away, but nothing of a concern that I would be aware of.
Okay, the wavelength which was asked for was near infrared. I don't know if this helps for.
Yeah, so at least what I can say in the near infrared area, we have intensive color technology on how to maybe, for example, make a black polycarbonate sheet that is sensor transparent in IR. And there you even get specifications on the transparency at a certain wavelength. And there are different colors actually specifying that, for example, for LIDAR applications and automotive applications. And I would highly doubt that you have problems with autoluminescence here. No?
Mm-hmm. Yeah. Thank you. This is also in the chat. Thanks. I would also have one question. This is effect with the optical behavior of the grade which has a flame retardant property. You mentioned the transparency. What is about the light guiding behavior? I know that you have some grades which are quite good in terms of light guiding performance. How is the light guiding performance affected by this additional additives?
So let's say in direct comparison to the let's say light LED grades that we are offering, it's standing a bit behind that. That just from the nature of the technology that we are using, it can't get these absolute superb light guide properties. I would have to look into detail into what it can achieve, at what kind of length this, how much light you can actually retain. I need to look into these details, and we can follow up that maybe after the call. But it's definitely not up to the limit what current products can achieve.
Mm-hmm. And one more question regarding the service of Covestro. Basically, Covestro offers granules of the materials. If I want to design a new product and I consider using new grades of polycarbonate, so microlone, is there any service which you can provide? Because it is difficult if you just have the granules and you're not capable for, well, making parts of it, at least half parts.
So basically, a good question. We offer the full support, so to speak. So it could even start in the idea phase, ideating around new technologies, new ideas, then going into mold design. How do the mold need to look like that it works well with polycarbonate? Assisting in how do I need to run my processes even on site if you have some issues processing our materials. Obviously, step before, which one is actually the right material go into our applications. We offer basically the full support along that chain. And specifically, if you have questions, either here related to lighting, you can directly reach out to me, or which works very well is if you go through our website, contact us through the website portal that is very well rooted into our companies and into the right experts.
Okay. Well, thanks. Good to know. Well, so then, thank you again, Mr. Grote, for this good and interesting insight into your microlone world. So then we come to the next agenda topic, which is, as I mentioned before, moderated by Jose. Jose will take over now. He's the Director of Technology and Innovation of EPIC, so the European Photonics Industry Consortium, and he's perfectly integrated in the European network of photonics. And therefore, I'm very happy that Jose will be the moderator of this company pitch session right now. Jose?
Not as happy as I am, Christoph. Thank you very much for this opportunity. Indeed, yes, I work for EPIC, and everybody knows EPIC. I'm not here to talk about EPIC. I'm here because between Covestro and SABIC, two amazing companies developing materials, I wanted to bring 4 CEOs of companies who, in my mind, have made a difference of micro-optics and optics manufacturing using the right materials. And I want to hear their story. I brought 4 CEOs with me. We have Ruth Huberts. She's now ThinkMade Engineering and Consulting, but we all know her from the amazing trajectory of Multiphoton. Jürgen Sousel, the CEO of Forafol, Mark Wielands, the CEO of Wielands UPMT, and Martin Herzweiler, the CEO of Nanoscrib. I always get happy when I say the word Nanoscrib. We have 4 people, 4 companies here who have made a difference with the polymer material, and we're going to ask them what else can we do for them to make them even greater. So let's get the show started. The first speaker requires no introduction. Ruth Huberts has been one of the drivers of the to photon polymerization revolution that industry has been living in the last years, and has been one of the drivers of bringing micro-optics manufacturing to all the applications from the bio to the consumer. I want to hear from her a bit of her story. It's a pitch of 7 minutes, and most important, what can we do for her and what can she do for us? The floor and the attention of everyone goes to Ruth Huberts. Thank you very much for this. Ruth, you are muted. Yes.
Thank you very much for your kind introduction. So I hope I can share the screen now. Doesn't work. It works.
I'm sure it will. Let's try.
So of course it will. It always does. So why not today? Whoop. You see the full screen?
It is coming. It's coming from Würzburg.
Man,
beautiful
this is
road.
slow.
It's here. The floor is yours.
It's there. So thank you very much, Jose. So I'm talking about materials for lean processing in the optical materials sector, and I devoted most of my life to the hybrid polymer materials, and the reason for that is very simple. So the reason is that you can tune the properties between glass, silicone, and polymer materials. So it's a nearly infinite class of materials where you can adapt the properties by chemical design. And here is a so-called oligomer from a multinuclear NMR measurement. And what you can do with these materials is you can actually cut down the number of processes you may need to create a certain element to a minimum at 3. So starting with a coding process, a structuring process, and a development process. And there is no matter whether you consider one photon processes like regular UV processes, or whether you use 2 photon processes. So this doesn't matter. This is basically the same. And I'm very happy to have this partner on my side for now then 21 years almost. It's micro-resist technology, and I was one of the first customers doing E-beam back in 1993 or so with the materials from micro-resist. So what can you do with the materials? So UV lithography, you can do standard lithography, and this is a very old example for single mode and multi-mode waveguides. So this is an example I did with Fujitsu. This is an example we did together at my time at ISC with Thales and Fraunhofer IOF. So with a very low loss variation horizontally and vertically in a stack like this, and this was packaged to this element. What else can you do? You can do UV assisted replication, and that was published, I think, in 2006. So this is also a very old example, but at the same time, it's a very good example of wafer scale optics. So now we're just launching a publication where this was shown up to 8-inch. So you can basically create your elements directly on top of the emitting surfaces of a LED or of whatever. Here is an example of a VCSEL array, of a 2x2 VCSEL array, where we did the coupling. And finally, you can do projection lithography. So we have shown that you can really enlarge the area on where you can create single mode and multi-mode waveguides, and this all was awarded by the Stifterverband. The next thing is nano imprint lithography, and that is an example which we did in 2009 to 2013. In a project called Metachem. It was a European project where we created large areas of hexagonal structures with very thin wall sizes and very low height for nano imprint tools. And here you see some example on the color which you can actually create by the individual structures. And that is an example of a microfluidic structure of Fernandez Guestro, where you get channel widths of about 30 nanometer by using these typical hybrid polymers, which are product of micro-resist technology. Finally, to span the entire way is one photon direct laser writing, which was done in '98. So I was not there at the Fraunhofer at that time. So this is a very old example, and I scanned that in. And a new example out of the range, which is not an optical example, but with an optical material, is a scaffold for orthopedic applications. And there is was a press release of my company Multiphoton end of last year that they achieved a cubic centimeter in about less than 1.5 hours. And that is very amazing because that was done with a material which was developed by IBA. And this is a material, or two types of materials which are biodegradable. So you can directly grow the cells on that and use that. So yeah, I have to move these people on the screen. So the magic epic question. So ThinkMate is a new company where I offer as a freelancer all my experience in any type of technology with any type of material. So this is not only hybrid polymers, but also ceramics, metals, semiconductors, you name it, with starting from E-beam up to wafer scale, 1 photon to 2 photon to whatever you would like to see. I started my third company and I'm just starting cooperation on Saturday with some people, which is committed to sustainability. So we'll see that one. I'm on more than 120 patents with, I think, more than 32 patents in multiphoton. This is the number of publications is very low for such an old scientist, but it doesn't matter because I have other focus. And I really cannot name the keynotes, talks, panels, mentorings, monitors, project, reviews, and coaches I did so far. So this is what I can do for you. What you can do for me is very simple, challenge me. So give me something to eat, which is a real challenge and a problem which you think you cannot solve. So I will most likely have a solution for that. And there is some other notice I would like to give you on the SPIE industrial session, which is a live session in 2 weeks or so. Yeah, 2 weeks. So I will be there together with many other people. And I would like to acknowledge, of course, all my co-workers on the examples I have shown you, which is microresist technology, Fraunhofer ISC, IOF, Thales, Acreo, University of Linköping, Carl Zeiss, IBA, and Multiphoton Optics. And here is the references, and I'm open to your questions. Thank you so much.
Thank you so much, Ruth, for this great presentation. Thank you for this very beautiful pitch. And today we have in the room a lot of companies who are actually developing material. It's a materials meeting. So I'm going to ask you if you could ask Santa Claus for the ideal material. Challenge the audience. We're going to challenge you later, but challenge the audience with this material that you think you need and you couldn't get yet.
I can get whatever I want to because I'm used to develop the materials together with the processes. So the ideal material, so when you look into the commercialized material we did so far, which you can get at microresist, this is also a very, very good example, like the ormocomp of a material where you can actually increase like 4 to 5 functions, different functions, and just end up with one layer doing many of these functions, which means that you can either reduce the interfaces in a device, which is very important if you look into the yield, and you can reduce the amount of material you use, which is important with respect to sustainability, as well as the amount of processes. So the ideal material would be, and actually you can do injection molding also with the hybrid polymer materials in a different way than with the thermoplastic materials. But that will be ormocomp in a injection molding, in a simpler injection molding possibility. So that is what I think. But I think the other applicants and the companies have much more interest in letting me know what they need, and probably I can find them a solution which is very simple.
As you say in your presentation, you have made quite a lot of emphasis on bringing, for example, integration of VCSELs for many different applications, even towards the consumer market. Have you ever encountered problems with the heat dissipation? Do you have any problems with the heat transmittance of the polymers? Is that something that ever happened, or is never the issue?
No, actually, this is quite reasonable. So when you think in terms of LED produce heat, yes, and the heat conductivity of the atmosphere is a little bit better than for PMMA. But when you consider the let's say the size of the element and the heat stability of the material, I would not say that this is a problem.
We need to move on, but before that, there is a question in the room from Francois Debuil, all the way from Belgium, from Dow Silicons. Francois, what's on your mind? Tell us yourself. I don't want to read your question. Francois, yes, unmute yourself and tell us your question.
All right. Sorry, I was thinking you will raise.
I prefer you do it. Much better.
Okay. So, Ruth, you indicate a triangle, glass, polymer, silicone.
Yes.
Can you provide example of hybrid material, any of these combination? I mean, two of these maybe, which is used in optics today. I mean, can you have an example that you have worked with?
I think I showed many examples. So many of these examples are in other form, in many consumer products, and also in automotive applications. So what do you mean by show an example?
Yeah, but you show a triangle, and the way I understood this triangle, you show material B, A, etc., a combination of these polymer, glass, silicone. I interpret that as being, well, you may have developed or worked with hybrid material, let's say between silicone and a polymer, and then what polymer? Because polymer is quite vague.
No. This is differently. So I put up this slide. So you have.
How should we interpret this slide? Yeah.
So you have an inorganic organic backbone, and this is organically functionalized. And the way on how you are from Dow, you should know that. So I don't explain
that, absolutely. Right? But that's why I'm asking the question to you.
It's a physicist explains chemistry to a chemist. So what you basically can do is you can tune the possibilities of the materials you create to any of those directions. So you can have materials which are completely bendable and stretchable.
I think you need to have a follow-up discussion. I know Francois very well, and he's the kind of person who would love to talk to you. It is a pitching session, so we need to move to the second speaker. From Würzburg, we go to Jena. We go to Jena because first, it's the capital of optics in Europe, and second, because a company there called Orafol Fresnel Optics. Orafol Fresnel Optics made a big difference in the solar industry, and then they reshaped completely their business to make Fresnel optics for many different applications. We're going to hear from the manager director of Orafol, Mr. Jürgen Zossel, about the technology that they use today in Fresnel optics, their materials, and most important, how we can make them be even greater. Thank you so much, Jürgen, for being with us this beautiful afternoon. The floor and the attention of everyone goes to Jena, goes to Orafol Fresnel Optics.
Okay, thank you. My name is Jürgen Zossel. I just cannot share the screen as long as the other one is still in.
We need you to stop sharing your screen, and then Mr. Jürgen Zossel will. So we have Ruth right now muted and sharing the screen. So I'm going to kindly ask the organizers. I'm going to ask the organizers to stop sharing Ruth Hubert's screen. Helen or Francois, Helen, Christophe, could one of you stop sharing Ruth's screen, or Ruth yourself? This is the problem we do in the meetings live. You record them, but you don't have the same kind of interaction between the people. We organized a meeting on solar industry a few weeks ago, and it was great to hear Orafol. Christoph, we need somebody to stop. That's fantastic. Thank you so much. And now we go back to Orafol Fresnel Optics. Thank you, Jürgen, for this. The floor is yours.
So I hope my screen is there.
Crystal clear.
Yeah. Okay, my name is Jürgen Zossel. I'm managing director of Orafol Fresnel Optics in Apolda, which is close to Jena. We are a lot of optical companies, and we are focused on microstructured optics from very small parts up to 1 square meter. Okay. We are a partner from Orafol, and Orafol is focused on the roll-to-roll process for films, but they are also doing film for microstructures, and our focus is more or less just an optical component. And they are all focused on microstructures for different usings, for the display market, for sensors, for lighting, for machine vision market. And we also had a time, we used it very often for the solar market. What we are doing is we have a compression and an injection compression molding process as our main and most important process in-house. This means with compression molding, we are using big presses since close to 50 years. Meanwhile, developed all this machine and all this process by ourselves. And with this process, we are able to generate micro or nanostructure. We can do their very large parts up to 1 square meter, but we are also able to use these big dimensions to use, for example, a multiple tool to replicate a lot of small parts in one blank, which will be in a next step trimmed into the single dimension. And if we do these small parts, we also have the other option, not to use just the injection, just the compression molding. We can also use the injection compression molding, but injection compression molding is not a standard process what we are using here. At this point, we did spend a lot of time of development to generate their very similar process to the standard compression molding process, which is also included in a variotherm process. And with this process, we are meanwhile at the same point to generate very precise structures, which is the most important thing for us. And in both processes, we are using for sure polymers. You see it in the center. It is what we heard already a couple times. We have there I think done very good developments, for example, with the company Röhm to development a very special optical PMMA in the range of the 8N, or we are using the Macrolon from Covestro. The special thing is that for every part which we are generating, we are using a heating and a cooling process, which generates the very precise structure. And after these structures are generated in a special blank or a basic blank, we have the option to do product enhancement, to put interference layers on, to put a metallization or anti-scratch coating. And we are also able to generate a anti-reflective nanostructure by ourselves in the basic polymer material, but we also did already replicate this structure into a final tool which we could put into our molding process. In an additional process, we put every blank which is done in the molding process in a CNC trimming to generate the final dimension. And after this step, we have a 100% inspection. This means every part which will leave our company is inspected. It could be then manual, but meanwhile also in an automated process. In addition to this, what I talked about, the polymer, we got focused on the precision verification for silicon on glass for the CPV market. Here we did produce very large lens arrays on a big glass substrate with a silicon, and in the silicon we found the structure. Meanwhile, this process is also used for some special optical components. Where these optical components are used, very important for us machine vision market. Everybody may know this, to inspect a bottle or a box of bottles. You see here optics from our side. Here, for example, to look on the big box of bottles, we have here a transmissive system, or We have here inspection system, for example, with big cylinder lenses. Or on the other hand, we have here very small lenses, for example, for very special sensors. We are involved in the display market with light guides, or in the head-up display with special diffusers. In the lighting market here, for example, with standard Fresnel lenses, which are included in a very big combination. Or here we see reflective lenses. It's looking pretty small, but one of these lenses, for example, is more than 1 meter in the diameter. So these are the typical markets. And if we would like to go forward, we have every time the option to generate a new design. We put after design is generated, we are able to build up a first prototype or to generate a very precision master tool. And with these master tools, we go into a tooling tree. This means after we have one time generated such a master tool, we replicate it in a electroforming process into a next generation, with a matter generation and then a temper generation, which is very helpful for the customer for the future. Because with such a tooling tree, we are able to support the customer for the next 10 or 20 years. And I think a very helpful process, very helpful for new products. So, thanks.
Thank you very much. I still remember when I went to visit you in Jena, we actually went through the facilities. I was amazed by the capacity for production, the large capacity for production, and also how you transfer the business from the solar to the different industries. I also remember when we saw your demonstrator at the Vision show in Stuttgart, when you were actually reading the labels of bottles from the top with the Fresnel optics. That was really, truly fantastic. Congratulations. We have questions for you in the room. The first one is coming from Heidelberg Instruments. Thank you very much for being with us today, Dominique. What do you have in mind? Dominique Collet from Heidelberg Instruments.
Yes. Sorry. So I've just heard that you made some large area, like up to a square meter. I've heard in your presentation, and I was wondering how you generate the microstructures on this kind of large area.
So what we are doing here, we are able to generate the own microstructures in the range of 550 millimeters by ourselves here in Apolda. This is a capacity what we have available for larger components. Sometimes we cooperate with a partner. On the other side, we are using special arrays. This means we combine single lenses to a large dimension, and at the end, you are very fast at the point of 1 square meter. So it every time depends what the customer does need. For sure, as larger the structure is, as more difficult, as more is the challenge to generate such a structure.
And what kind of height are the structures made? What is the height of the structure?
The height of the structure, it starts off about 1/10 of a millimeter to 3 to 4/10, maximum 5/10. Mostly we try to keep the structure not too big. It depends a little bit from the application.
Thank you. Yeah, thank you very much, Dominique, for that question. Also, congratulations. Heidelberg Instruments is really a fantastic company in the massless lithography and also in the writing for the manufacturing of micro-optics. One question before we close with you, Jürgen. This is a meeting that actually brought together many material suppliers for the manufacturing of molded optics. Is there any material, any request, any challenge? You could choose the fantastic ideal material that you could never get from this industry.
Yeah, I think the material or optical polymer is every time a huge challenge, because I remember about 25 years ago, we developed, I would say, also for still today, the best material which is available. It's a PMMA, and the big challenge for us is to release this material from a microstructure, because it's very hard, as long as you have not just the slope, also a draft, which is very hard to release the material, and therefore we have special releasing components in the material included. But on the other hand, you should not see this included releasing material in the optical component, and it should not include the transmission. So it's very, very hard to find there the right material.
Thank you so much, Jürgen. And now we go from Jena to Liège. We go to Mark Wieland, who is the CEO of Upmt, one of the most innovative companies I have seen in freeform optics, freeform micro-optics on both sides of the optics. You will see what I'm talking about, because if you are as excited as I am, there is lots of business opportunities here. Mark, thank you very much for being with us this afternoon. The floor and the attention of everyone goes to Wieland's Upmt.
Yes. Hello.
Let's go to share your screen, which you're already there, but we need to see the presentation.
Yes, I'm trying to get it there. So here it is. Can you see it?
Crystal clear.
Okay. So thank you, Jose, and thank you also from Fraunhofer to let us this opportunity to present our small company. Wieland's Upmt is a Belgian company, startup, still 8 people in the area of Liège, and we are, let's say, we are active in ultra precision machining and molding technologies. So we are, let's say, part of the company is an engineering company where we try to develop technologies that solve a known problem, and when we come up with let's say an innovative solution, then we try, of course, to commercialize this. And all the applications that we are focusing on are mostly about lens arrays. So we saw that a lot of applications in optics were concerning lens arrays as of the function of the array being optical or being many lenses fabricated at the same time, so for economical reasons. So we started a few years ago to develop a first technology which is related to diamond turning, ultra precision machining. And so we thought, okay, yeah, well, many people are talking about machining lens arrays. How do they do that? So we saw the state of the art and thought, if you want to have, let's say, the lens arrays with the best quality ever, you would machine every single lens of the array as a single optical surface and bring it on the center of a turning lathe. And that's where you get the best roughness and also the best form accuracy out. So this was an unsolved problem, which we solved a few years ago. We called it dynamic part indexing. It's a patented technology. It allows us to machine very efficiently and very accurately masters or lens arrays in metals or in PMMA in a single process without ever stopping the process. And this with positioning accuracies of a micron over an 8-inch wafer, and also form accuracies like you can obtain from turning. So a few, let's say 100 nanometer, 150 nanometer PV on these surfaces. So I have put here on the side a bit all the, let's say, the characteristics, but people that know about ultra precision diamond turning understand that you can make A-spheres or even freeforms with this technology. Of course, you can do diffractive structures, Fresnels. Yeah, okay. So typically people, our customers use our services to make a master for a replication process, for example, polymer glass or things like that. And so the quality that comes out, what's very differentiating is the roughness, which is really nanometer level. It's depending on the material, but mostly we use nickel phosphor, and then we can get to 2 or 3 nanometer roughness. We have a big degree of freedom in sizes. We say over 10 micrometer, but this can be really much bigger. In the very small micron size, we are limited by the tool which has always a certain dimension, of course. This technology, we are always continuing to develop it so that we get to, let's say, tighter and tighter specs. And nowadays we are capable. So here is set MLA to MLA over the surfaces, 2 microns. Yeah, we are getting this down to 1 micron. Okay. So besides that, we have been developing replication processes, but I wanted to show here in this image still, an image of an 8-inch master. Most of the time I cannot really show it because it's customer related, but this one, let's say we did ourselves, so we are allowed to do it, and you can see that the achieved form error was about 20 to 30 nanometer RMS on the surface of all these lenses. And all these, what's nice is that all these lenses are identical all over the surface. Okay, so this process is running sometimes over days, sometimes over weeks. Okay, to put like 10,000 or 100,000 lenses on the same surface. Then we have developed also some, let's say, processes for replication, which are making profit out of this machining technology. So using our own mold inserts, and this is to process all kinds of thermoplasts, macron LED, which is really a standard material. We heard it before, but this is really like that. EP from Mitsubishi, or Able from the COCs, Able Topaz, or the Xeonexes. We've been processing all these in 2 processes. So we have a 1-step process and a 2-step process. The 1-step process is a wafer format injection compression process, and it allows us to mold wafers to a size of diameter 150 about maximum. And so we have a number of structures inside that wafer that are then later diced or after the coating. And again, the roughnesses are low, and the SFE is a little bit higher here in this process, but this process is extremely efficient. So with low cycle time. So we have built a standardized tooling setup where only the structures are modified, and of course the process is adapted to the structures every time. When that quality that comes out of the 1-step process is not sufficient, let's say there are limits, of course, to injection molding. If you go to extremely thin lenses, then the process ideally becomes a compression molding process, and that is what we call the 2-step hi-fi optics process. It allows us to make that kind of very small CCM stacks, self-aligned, because the optical surface and the alignment surfaces are molded together, micron accurately aligned. And this allows us to overcome the limitations of classical injection molding. So the higher aspect ratios, up to 8 that we have done, thin sections below 200 microns, very high slopes. It's a slow process, but because of our technology for the mastering, we do many lenses at the same time. So we produce these in wafers where there are hundreds of lenses in. And that's the way the process at the end becomes, let's say, economic. Applications for the 1-step process, MLA, lighting, time of light, LiDAR, diffusers, disposable endoscopes, these kind of applications. And for the two-step process, CCM, miniaturized CCMs, like for AR, medical and defense. We come to the end, and the epic question, what can we do for you? Of course, we can make masters for companies that need the masters, like the replication companies. We can also help with the production of full plastic lenses that are molded by our hi-fi optics technology on a wafer level.
Mark, I'm going to leave this slide up because we have a lot of questions for you, and I really think these are great business opportunities. So we're going to very quickly through the questions. The first one is from Sven Kravenborg from BASF Coatings. Sven, thank you very much for joining us. What do you have in mind?
Hello, Mark. Thank you for your pitch. I had just a short question. Do you also have experience or offer these ultra precision structuring on a drum, on a roll-to-roll drum?
Yeah, we have done that already. Yes, we are. Let's say we are. I don't know whether how much I can say about this, but within the project Fabulous, we have one application where we machine the structures on a drum. This can be done. Yeah.
Okay, we have a lot of information about that from Fabulous. We can share with you that in an email. The second question is coming from Dow Silicons, Francois de Buil. What do you have in mind?
Yeah, my mind was if you had any experience with silicone, optical grade silicone. I mean, you refer to optical plastics and thermoplastics. So.
Yeah. Well, no, no, we have no experience with silicone.
Okay.
The third
any
question.
Interest on your side?
Sorry?
Any interest eventually for a given project?
Yeah, maybe, but yeah. But
okay.
Most of the time we follow, let's say, the choice of the material is most of the time done by the customer.
Makes sense. Okay.
The third question is coming from Savik. Gabriel Hoagland, what do you have in mind?
Yeah, sorry that Jose cut you short on the bottom of the page with the high temperature thermoplastics, but I think I'm going to talk about it in a minute.
Yeah.
But my question is actually, indeed, the aspect ratio on the diffractive pattern is very good, right? Do you think it's detailed enough for face recognition or other biometric sensing?
Yeah, so we have done, let's say, applications for, let's say, 3D sensing with this technology, and yeah, that's possible.
Gabriel, yes, this is yes. But I think Mark and I cannot share more about this, but yes, definitely. I would like to move to the next speaker, but before that, I would like to say, Mark, you've been great. Congratulations what you're achieving. When we go to the next speaker, I have to stand up. I go to one of the companies who's making a difference in this ecosystem. I go to Karlsruhe and I talk to Nanoscrib. Martin, thank you so much for taking the role of the closing speaking of this fantastic pitch session. The floor and the attention of everyone goes to your great two-photon polymerization. The floor is yours.
Thanks, Jose, for having me, and thanks also to the organizers of the Aachen Polymer Optics Days. So let me give a brief introduction to Nanoscrib. My name's Martin. I'm co-founder and CEO of Nanoscrib. We have devoted our mission towards additive manufacturing of
Martin, we still don't see your slides. Just to give you a heads up, just in case you wanted to, okay.
Here we go.
Fantastic, yes, beautiful building.
You can see that? Good.
Crystal clear.
Thank you very much for having me. Just a quick glance at Nanoscrib. We are a group of about 80 people, 40% of which are working in research and development on additive manufacturing on the micrometer scale. So last year, despite the Corona pandemic, we grew 40% in revenues year over year. We have a deep expertise in micro-optics and integrated photonics. As a proof, we have 4 funded projects currently running in the integrated photonics area, and a lot of people, 40% work in research and development. Overall, we have more than 2,000 system operators worldwide running our machines, and despite our headquarters in Karlsruhe, Germany, we have subsidiaries in Boston and in Shanghai. Right now, our customer productivity on the academic part approaches 1,000 publications achieved with our devices. We have two major product lines in terms of systems. One is to the left side, the research and prototyping tool for 3D additive manufacturing. That's the Photonic Professional GT2 system. That is the product in its third generation. We recently launched Quantum X as a new pure industrial device for maskless lithography and additive manufacturing on the micrometer scale for industrial users with best-in-class throughput, accuracy, and precision. And to provide a holistic approach to a solution, we also provide the resins that make sure that the printed results achieve astonishing results. So just at a glance, two-photon polymerization as an additive manufacturing tool on the micrometer scale, it bridges two different worlds. One is the lithography world, that is anything that has to do with two-dimensional micro or nano fabrication, and the other aspect is 3D printing. And we are somewhere in between these two worlds. So a matrix of what can be done with our machine spans from 2D lithography to 3D additive manufacturing. It goes from the nanometer scale up to the meso scale. If you're interested in the technology itself and want to spend some time on interesting literature, then I invite you to register for the download of our white papers. So we have a section on our website where you get access to about 20 pages long documents on two-photon polymerization and two-photon grayscale lithography. Just to shed some light on what you can expect there, you will get explanations on the two-photon polymerization principle per se. I'm not going to explain it here. Two-photon grayscale lithography that drives the performance, especially in the category of micro-optics and diffractive optics. So these exemplified pictures are just to create some appetite if you find some time to have an interesting read. So what are the benefits in micro-optics? To keep it brief, first of all, it's the design freedom that two-photon polymerization offers. May it be of replicable curved surfaces that sort of have a 2.5 dimensional topography for mastering and replication. These masters can be used for either injection molding, hot embossing, nano imprint lithography. I'm not going into details here, but these are current standards for next generation products to come to the market. Our industrial customers use Quantum X in order to fabricate these polymer masters for replication. Then you can, of course, go beyond with 3D geometries, with unique things like very high filling factors, sharp edges, hybrid optics. You can staple these optics like a triplet lens or duplet lens. You can do that basically anywhere you want it, may it be on a fiber tip, on a wafer, or on a chip. And the beauty of additive manufacturing is that you can do quick iteration cycles and prototyping. And we have also the ability to scale things up. The process steps are quite simple. Just to shed some light onto three types of objects that maybe go beyond what you typically expect. One is diffractive features on top of refractive structures, so-called hybrid lenses can be additively manufactured, or diffractive optical elements that go beyond the economical compromise of 8 layers, but you can also go to 4,000 layers if you consider the two-photon grayscale lithography approach without investing too much time. And you can also do things like angled diffractive optical elements, blazed gratings, blazed DOEs that have a superior performance than standard DOEs. So let me draw the attention to the epic questions. What can we do for you? What can you do for us? We can do for you feasibility studies. If you have a specific idea in mind, just challenge us, send us an email, give us a call. We are ready to evaluate your ideas. We can also test and qualify interesting new photoresists and resins and make them maybe the next standard for two-photon polymerization. What can you do for us? I think if you provide innovative replication techniques for micro-optics, diffractive optics, let us know. We would like to evaluate our masters for these replication techniques. If you have superior measurement instrumentation that allow us to see more than we can currently see for micro-optics, then we'd be happy to evaluate your measurement techniques. The challenges that I currently see is that the design software tools do not incorporate the design freedom that two-photon polymerization and two-photon grayscale lithography offers so far. It's more like based on electron beam lithography, digital topographies. It does not fully cover the abilities of two-photon polymerization and two-photon grayscale lithography. And the outlook is, once this is incorporated in good design software that is easy to use, we will also harvest vast innovation potential of two-photon polymerization. So I invite you to seize our technology and innovation know-how, to contact us, and that we discuss your design ideas for feasibility. Thank you.
Think big, print nano. Thank you so much, Martin, for this. And I would like to highlight that item in the EPIC answer to the EPIC question, in which they say they are willing to test, to try materials. So if you are a material supplier and you want to find a nice R&D cooperation to test whether your material is suitable to two-photon polymerization, this is a key opportunity. We have a question for you in the room from one of those companies, from BASF. Sven, what's on your mind?
Thank you, Jose. Thank you, Martin, for the nice pitch. Well, I'm not going to ask a materials question. I'm sorry. I would know a little bit more. What kind of RMS surface roughness can be obtained with two-photon polymerization or two grayscale polymerization with your machines?
So better than 10 nanometers is a standard. Typically achieved is something like 6 nanometers.
That sounds very good.
Surface roughness RA.
Yeah, that sounds very good. And what kind of feature sizes can be obtained?
It depends. So let's say feature sizes, it's difficult to grasp. Do you think of micro optics or diffractive optics or?
Nanoscale, I was thinking about.
Nanoscale. So let's say for diffractive optics, if you think about a pixel that can be sub-micrometer, so these are typical size scales, something like down to 500 nanometers rectangular grid size of pixels. That is a good standard.
Good. Thank you for your answer.
Martin, congratulations on what you are achieving. Congratulations on the fantastic year 2020 despite the pandemic. This is really to show people that things can go in the right direction. And I would like to also thank all the 4 friends, all the 4 CEOs of great success stories that I brought together with me to this amazing event. Christoph, thank you so much for this opportunity. I loved every minute of it. If anybody wants to get in touch with any of the participants today, just send me an email. I will make the introduction. Back to you so you can introduce SABIC, the thermoelectric material that we all love. The floor is yours.
Well, thank you very much, Jose, for this good moderation, and thank you everybody who presented this company pitch. I think it was very impressive, and as we see, there are many points where we can come later together. I think it works perfectly for networking through these companies. Well, now we come to the next presentation presented by Gabriel Hoagland, who studied organic chemistry with a focus on plastics. He joined SABIC in 1991 with focusing on developing new thermoplastic resins and blends, both as a scientific as well as a product manager. Since 2013, he's responsible for high heat material resins, and I'm looking very much forward to learn about more about this innovative material class. So, Gabriel, the virtual stage is yours. You're still on mute. No, still we don't hear you.
Somebody unmuted me.
That's good.
Sorry about that. Okay, yeah, before we do that, let me give a brief explanation about the company. I think SABIC is not so well known, like for instance, Covestro, but we are a global leader in chemicals. We are headquartered in Saudi Arabia, but obviously we are a global company, so we have a lot of global locations. For instance, I'm in the southwest of the Netherlands, where we have the European technology. We have 4 different business units, and the one I'm going to talk about is Specialties BU, where we produce differentiated polymers, as you can read here on the page. And actually, they are positioned in the famous thermoplastic pyramid on the top. So these are the products I'm going to talk about today. Let me see. And of course, there are a lot of other polymers that we produce within SABIC, but they are mostly produced in the other BUs. So all the way in the bottom, from let's say the standard bulk polymers, polyolefins, polycarbonates, like the polycarbonate that my colleague of Covestro discussed, all the way to the, let's say, the left side of the amorphous pyramid, which is still transparent and has very high heat performance. But before we do that, I'd like to start with a trend in the electronics industry and how molded optical polymers in general can have a part in that trend or even help solving a problem. As you probably know, in today's world, there's a lot of sensors, right? I mean, simple proximity sensors are used in phones, but also more complex face recognition and gesture controls in cars, inside or outside with LiDAR. And to collimate the light between the laser, but also the detector, you always would need a lens. But these lenses need to be produced in millions per year for each model. They also need to be small because, you know, miniaturization is another trend in this industry, and they need to be cost effective. So it is really something, and I think most people on the phone will agree with that, a very interesting area for thermoplastic optical resins. And here I just have one example of a proximity sensor where you can see the size of the lenses. So, you know, these are 2 lenses, one for the emitter and one for the receiver, which are partly overmolded with the black polyamide and then assembled in a proximity sensor into a phone. And I think that is used still in a lot of phones today. So the challenge for these lenses are really threefold. Of course, they need to be transparent. You know, you should be able to produce them in a cost-efficient way. You also should be able to make free-form optics, which is of course very easy to do with injection molding, like aspherical lenses. But there is something else in this industry. In the semiconductor industry, an often used assembly technique is reflow soldering. So that means that actually the lenses need to survive reflow soldering, which is another word for surface mount technology. And for those of you who do not know what that is, actually it is depicted on the bottom of this page, where the components are put on the PCB with a solder paste. And then, because the solder paste these days are lead-free, you need to go to a pretty high temperature. I think this is the typical GDAC protocol, that you go from room temperature to 260 degrees for 10 seconds, which of course is, you know, very harsh for most of the standard optical polymers like PMA or COC or PC. Within SABIC, we have Xtum, and again, this is again the top of the pyramid I just showed a few pages ago. Xtum is a thermoplastic polyimide resin with a TG up to 280 degrees Celsius. And it does withstand reflow soldering, right? Because the TG is 20 degrees higher than the reflow solder temperature. We also have other polymers. I'm not going to talk about it today, but I just mentioned a few of them, which are also used quite a lot in this industry. Ultim is very well known to a lot of you. TG is a little bit lower, but Ultim is used a lot in optical transceivers because of the high dimensional stability, so the low CTE. And we also have let's say a copolycarbonate, similar to Covestro, but a little bit different chemistry, where you can increase the TG up to 195. This is water clear, and is used for lenses like, for instance, flash lenses, where you really want to have water clear transparency. Now, one drawback of Xtum, you already see it in the picture, is that it is a bit amber brown. So you cannot use it for water clear application, but for a near infrared transmission, so 850, it is no problem to use. It has, for instance, 80% transmission at 1 millimeter at 850 nanometer. This page is a little bit of quite a busy slide. I think it's more for your reference if you want to take a look at it later. The refractive index of Xtum is relatively high compared to glass, 1.63 at near infrared wavelengths. Of course, there is a dependency on temperature. So the DNDT of actually any plastic is always a disadvantage versus glass. So the slope of plastics is roughly one order higher than glass. But optical designers can work with that. Here's the transmission again. I mentioned 80%. That's what you see here on 1 millimeter of Xtum. If you really want to increase that, think about LiDAR, for instance, where every photon counts, you can apply an anti-reflective coating. So if you put one coating on top of the lens, you increase the transmission with 5%. If you are able to also apply a coating on the bottom of the lens, then you go all the way up to 91%. It's still not like Ultum or polycarbonate or glass, but it's pretty high. Actually, optical designers do not care about these graphs. They only care about optical constants, and so that's why we have added the optical constants of our resins into a Zemax. I think I've seen it also already on one of the other presentations. Zemax is the most, let's say, famous optics studio databases that optical designers use to do simulations with. I think we are in since a few months. So those of you who are on the phone that have access to Zemax, you can take a look, and Xtum and Ultum should be there. All right, so now a completely different application, and well, Jose knows more about this than I. So, but if you talk about the PCB in a data center, right? I mean, everything in a data center is already with light fibers, but the final part, the PCB, is still with copper. And the copper has issues with the fact that you go above 100 gigabit per second. So with increased bandwidth, in the future we have to go there. Then you have to make the copper thicker and thicker, and there will be electrons jumping from one trace to another trace. So to avoid this crosstalk, there's only one solution, and that is to go fully optical, which means that the whole PCB will be covered with waveguides. But hey, this is a very disruptive change. It means a lot for the optical interconnects. Not so much for the faceplate. I think the faceplate, we already sell Ultum since many decades for the lenses here, and I think that will remain. And here is just a picture of an pluggable optical transceiver with an Ultum lens, both from the transceiving side as the receiving side. But more importantly, close to the ASIC, the application-specific integrated circuit, all the optical waveguides will bring the light into the ASIC. So here you need to couple the light into the detector. So to do that, there are a couple of ways you can do that. I mean, some companies, I think Broadcom announced last week a connector here, where they use grating coupling, or some people use pigtailing or butt coupling, but they all have their disadvantages. Actually, grating coupling is a kind of open connection, and butt coupling is very fragile. So in the data center, you want to have it dust-free and stable for at least 10 years. So we believe that Xtum is really a very nice solution to this problem, because you can make an Xtum connector with different lenses. I'll show you an example in the next slide, where you can couple the light from the waveguide into the ASIC and into the photodiode detector. But of course, then the connector needs to withstand reflow soldering. So we have a project with with Nalux. With Nalux is a molder in Japan, and a big OEM in the US, whose name I cannot mention, where we actually did mold an Xtum connector, you know, very small, something like 9 by 4 millimeter, but many complex optical features comes with it. So there are 4 lenses from the side, and also, sorry, 8 lenses from the side, also 8 lenses from the bottom, so total 16 lenses. From the right side, that's, let's say, the receiving side. So the fibers are plugged by an empty ferrule connector here with those 2 pins. The light is being reflected with an internal mirror. So this is metallized Xtum, 90 degrees to the die side. And the die side, of course, then transfers the light into electrical signal. And then at the other side of the connector, you have the transmission side where the light is being, sorry, where the electricity is transmitted into, with a laser into a light signal. So it's a very complex part that operates on a multimode wavelength like 850 nanometer. So the OEM in America said, well, you know, it is very important to have the lens-to-lens distance, and this is just a schematic diagram of all the different distances in the part. So number 17 to 32 are the lens-to-lens distances from the side as well from the die side. They should not change their dimension more than 30 micron after reflow soldering, because then if it's more than 30 micron, you would lose a lot of optical signal. So since we here at SABIC, we have our own reflow machine and our own confocal microscope. So we looked at doing reflow with this connector at 260 degrees Celsius for 3 times. And we see a negligible dimensional change. I mean, it's well below 1 micron. Well, remember the spec was 30, right? So this is pretty good. Okay, that's one thing. The other thing is, of course, what about the optical performance? What about the signal loss after reflow soldering? We see that we lose a very small amount of signal, only 0.1, 0.2 dB after reflow soldering. Remember, the total signal loss budget is around 3.5. That includes all fibers, all waveguides, all connections. So, I mean, 0.2 is acceptable for the customer. We also did not see any blistering or any visual defect. We also, of course, have to go to long-term aging performance. There's an industry protocol like Telcordia that dictates that your part needs to remain stable at least for 1,000 hours if you age it at 85C and 85% relative humidity. We have done some tests with optical plaques where we actually translated the transmission to dB. And well, Xtum does not get opaque or, you know, form blisters or whatsoever. So the dB loss is very minor. So that looks all pretty exciting. So a couple of other things you can do with molded optics, that is light manipulation. So I just want to show you a few slides on that. And I already heard about diffractive optics several times. What we have tried to do is use a nickel shim with a very complex feature size and do injection molding against that nickel shim. So you replicate the surface of the nickel shim into the thermoplastic. And well, we have done something like 530 nanometer depth with 350 nanometer distance. So, you know, this is not good for facial recognition. I think that's why I asked the question to Wieland. This is good for holographs. So if you put a light through this diffractive pattern, yes, you see that it works. But we're still in the process to use special molding technologies to get to a much finer surface replication, and to really get structured light that you can use in 3D sensing. Something that works very well is put a coating on top of our material, whether it's reflective or anti-reflective. Like I said, sometimes you want to have a mirror element in your connector, because the VCSEL, of course, gives you a vertical light that you want to bend 90 degrees into the die. Xtum and Ultum are very easy to metallize. You don't need a primer, so you can directly metallize it and get very good adhesion. And I already mentioned that you can also apply an anti-reflective coating to increase the transmission. This is very interesting. What you can do with any thermoplast is to add a very special organic dye into your thermoplastic material by compounding, and therefore absorbing all the light in the visible light. And it opens up at 700 or even at 750. So it's transparent at infrared light for the sensor, but it absorbs to a large extent, so there's even optical density of 5, the visible light. So why is this important? Well, you can imagine if you have an infrared sensor that there's a lot of stray light from the sun, and you don't want to have that light interrupting with the sensor accuracy. Of course, you can use a very expensive coating, but this is a much more cost-effective way to get this absorption in visible light. You can also use coatings for bandpass filters. So if you want to have, let's say, 960 nanometer VCSELs, and you want to have only transmission plus or minus 20 nanometers into that range and block all the other wavelengths, then that's something you can do with a coating. Of course, this is not so cheap to do, to be honest. Other things we can do with our plastics is overmolding. I think I already shown you on the first page this particular proximity sensor. By overmolding the Xtum with opaque polyamides, black polyamides, actually what you do is you prevent crosstalk. So you don't want the laser light from the emitter to be disturbing the reflected light into the detector. So that's a very elegant way to ensure that you don't have crosstalk. You can also use this plastic housing to glue the part on the PCB. So we worked with a couple of glue companies. I think one of them is on the phone today. We looked at different glue systems and different epoxies or silicons. Sometimes you want to have a transparent epoxy if you want to glue the transparent material. But if you glue an opaque material, that is not so important. So as a summary, as a BIC, we develop a lot of new materials. I didn't talk about the material for Ultim. For single mode optics, we have to reduce the coefficient for thermal expansion. That is something that we're going to develop this year and will be commercialized. We are not only a material supplier, we also do a lot of design. Actually, I showed you a few examples, but we also have a list with micromolders in the world that have experience with molding Xtum. I mean, we talk about a TG of 280, right? So you have to go to 400 degrees Celsius to mold Xtum. So it's doable, but of course it requires some special equipment. And we do in our headquarters mold flow analysis, and you can see here a nice picture how you can predict stress by fringes in the ethical part. We have technologies to have better surface replication, like heat-cooled technology or injection compression molding. We also have our own in-house micromolder capability, so we can support customers with all kind of tooling advice. With that, I want to stop here. If you have further questions, you can always contact me, or you can click on one of those links. Thank you.
Well, thank you very much for this impressive presentation. I think the temperature level itself is very impressive. Are there any questions for Sabik? So far I've seen nothing in the chat, so that's good, because I would have one which is related to the temperature level for the molding process. I could imagine that there is a certain challenge for tools and dies and the thermal systems for the dies. Can you give some experience on that?
Yeah. As I mentioned, you have to go to, for Xtum, you have to go to 400, 390, 400 degrees Celsius. Also, you want to have a good surface replication, so your tool temperature as high as possible, but preferably 180 or higher. There are many companies who make micromolders. Arburg is just one of them, which have no problem to go that hot. I think the issue starts if you want to go higher than 420, because then you need to go, to conductive heating, right? Oil heating doesn't work anymore because you get all kind of issues. So it's doable.
Okay. There is one question in the chat. Neville Green, maybe you would like to ask the question yourself?
I think it's me. It's Markus Kramer from Via Optic.
Okay.
What would be your best material choice for longer infrared wavelengths above or in the range of 1500 nanometers? And did you compare that to special glasses?
Yeah, that's a good point. I think I did not show a graph beyond 1500. Let me see. Something like here. No, we are transparent until 2500. And after that, we come into the mid-infrared, right? So heat sensing. Yes. There we have similar issues as glass, I should say, that you have certain absorption phenomena. So it is transparent until 2500 nanometer. And then I think above that, we are not transparent anymore.
And do you see any advantages or disadvantages to other polymers, or is it for all nearly the same?
Yeah, it's almost for every polymer has issues above 2500 nanometer because you start to get into a kind of vibration mode for certain structures. I think polyolefins will do, right? Polyolefins don't have aromatic moieties.
Polyolefin parts we are already doing, but I think it's really in the range of 1500. And the reason is that I got some requests for special LIDAR systems, and they see some benefits in that wavelength range.
1500 should not be a problem.
Okay.
You can see it here. Yeah, it's still transparent.
Okay. Thanks.
Okay. Then there is one more question in the chat, which is related to the simulation service. Is this a paid service, or how does it work with SAVIC?
No, it is something we do for our customers. Mold flow analysis. If we have the CAD drawing of a specific tooling, and you can send it to us in a confidentiality agreement, then our engineers in India only look at it, and only they have access to the CAD drawing, and they can do the mold flow analysis for us. So this is not a paid service. We do that for free.
Maybe one question more if it comes to molding of Xtum. What do you think is the thinnest wall section which you can fill?
That's a good point. Yeah, the part that I'm showing here is 0.3 millimeter. You can see a big sprue, right, and a big runner, and gate design. If you have a relatively small part, I think this is a 4x3 lens array, it is okay to fill 0.3. We also have, and I cannot share that because it's confidential. We also have proof that we can fill 0.1 millimeter. But it really depends on the flow length, right? If you have a very big flow length, it becomes critical.
And with which mold temperature? Is it a completely heated mold, or what is it?
Yes. Yeah, the higher the better, of course. So we do, sometimes we use rock tool, as you probably know, but also with typical oil-cooled molds, with Xtum, we go to 200 degrees Celsius. Obviously, you want to be a little bit below the TG of the material, but the higher, the better.
But for 0.1 millimeter, the 200 degrees are sufficient?
Again, I mean, that really, not with the part that you see here, but with a very small part, we have managed indeed to fill 0.1 millimeter. So again, I mean, it really depends on the flow length of the total part. And sometimes there's also an overmold, then it becomes a little bit bigger again. So that's how you can also influence bifringens and all these defects. But maybe you can talk offline to me, and then I can share a bit more details.
Okay.
Okay. Well, then, thank you very much. I think this was very, very interesting. And now we will make a short break. We have, we will go on 5 minutes, so nearly 10 minutes break. 5 minutes to 4, we will go on with the next presentation. So we are back after the break. I'm sorry, it took actually a little longer than I expected. So it's 1 minute to 4 now, not as I mentioned, 5 minutes to 4. However, we will go on with the next talk given by Sven Krabbenborg. Sven Krabbenborg studied nanotechnology at the University of Twente in the Netherlands, and he received his doctorate degree in chemistry in 2014 in the field of structuring and chemical modification of surfaces. In 2015, he started to work at BASF Coatings GmbH in the Coatings Applied Research Department. And in 2017, he moved from the research department to this current position. And now he is head of technology of BASF's functional film division, which is called Funtex. I'm happy to get the new insights of the production of micro and nanostructured films by Nano Imprint technology. So I hand over the floor to Sven.
Good afternoon, everyone. Thank you, Christoph. Thank you for your nice introduction. Let's see if I can share my screen. I hope so. Otherwise, it will be difficult. Can you see the right presentation mode?
Yes, we do.
Super. Before that, I want to thank also the organizers of the conference for the chance here to present, and for the audience who is still here at this time, wanted to listen to my talk. Well, as Christoph said, I will be talking about roll-to-roll manufactured structures foils for interior and exterior applications. A little bit about a short introduction about the company I work at, so BASF. I can talk quite a long time about it. I also don't know what they all do. It's quite a large company, all the way from petrochemicals, small intermediates, small molecules, all the way to polymers and agricultural solution, care chemicals, and so forth. I work at BASF Coatings, belongs to surface technologies such as coatings and catalysts. A bit more concrete, what does BASF Coatings do? Coatings is in the name. We do car coatings for color, for protection, for corrosion protection. We do decorative paints for interior, exterior use, and we have surface treatment. That's stuff that you do before you put a coating on, like cleaning, degreasing, and stuff like that. At Coatings, there's also a business unit beyond paint solutions who does not want to sell paints, who sells, for example, foil solutions. That's where my team belongs to. So functional films. There are several teams of us working in optical application, transportation, renewable energies, and others. And one of those I want to talk about today, and that is Funtex. That's where I belong to. Functional textures, performance by texture. There are many interesting functionalities which can be brought in by giving a texture to a surface. At this conference, we already have seen several of those. To give a short introduction in the industry, for example, if you see here the screen, the screens on your screen, they often use brightness enhancement foils, which you see here as a triangular shaped ridges. You also have in office lighting, the light which is used there needs to follow certain norms that you cannot glare you. So there are structures used there for anti-glare performance. And if you're driving around and you see those traffic signs in Germany or almost everywhere in the world, your light of your car reflects on the traffic signs back to your eyes, which is done by microstructured retroreflective films. There are many in optics. We have seen several examples of them. There are many of them. However, if you look into nature, there are many more interesting structures and functionalities which you almost cannot find in industry or just on a research level. Here on the top left, I show a moth. And if you look closer to the eyes, they have a very interesting property. If you look at the facets of the eye and zoom more and more in, those have small nano bumps, which give an anti-reflective effect. Here on the right, you have several of you probably already seen it. It's a lotus leaf, which have a very hydrophobic behavior, which gives the functionality of self-cleaning. That comes because you have a nanostructure on top of a microstructure. Bottom left, we have a gecko, very nice, colorful, I would say. And those have the very fun fact that they can walk upside down on glass, for example. They have a very good adhesion to surfaces, which comes to their fiber-like structures on their paws. They have a microstructure and lengths in the tens of microns, but at the tips they have the nano-structured fibers. Together with their surface properties, they can adhere very well. Then we here on the bottom right, we have a very efficient swimming animal. It's a shark. And that is because they have microstructured ridges on their skin, which makes them have a very low drag while swimming through the water. Many of these effects are known in the literature. They are published, but you almost cannot find them. They're not being sold or not being used. There's almost always somewhere in the development process, there's a roadblock. You cannot produce it at a cheap enough way. Some real world requirements are not being met. For example, here with the moth eye, you can produce it. However, it's easily scratched. You can, if you want to put it on something which you can touch, it's scratched in seconds or minutes of normal use. We try to bring some of these interesting structures that are there at partners, at customers, in scientific articles to the market. That's one of the things we want to do. And one of the technologies, replication technologies we use, our main thing is UV roll-to-roll imprinting. Yeah. So very broad, easy and quickly explained. I mean, now looking outside, it's all sunny, but 1.5 weeks ago, 2 weeks ago, I think everyone remembers there was snow everywhere, at least in Germany and the Netherlands. And when you have a tire going through the snow, you get those tire marks. You mold the tire structure negatively in the snow. And that is exactly what we use also in UV roll-to-roll imprinting. Here on the right, you have here, for example, a foil substrate, can be PMMA, polycarbonate, PET. You put a liquid-like UV coating on top. You press it against a pre-structured drum, which also was very nicely shown in the movie before of Fraunhofer. I liked really the movie. When you fill these cavities of this pre-structured drum, you can cross-link it with a UV coating or with a UV lamp. So polarize the coating, so it's hard. And then you can demold it. And then you have a structured foil. Sounds very easy. Sometimes it is. Most of the time, it's not that easy. However, this technology offers quite a lot of interesting capabilities. Most of the stuff done in literature is done on nanostructures. You can, Morphi was such an example. Here on the left, you see an artificial diatom structure. This was a template. The people copied it in UV coating one time. You see here the scale of 2 microns, so really high fidelity in the nano range. And then here they did a second copy. So you can see it's a very good way to copy things on a nanoscale. However, this technology also has it in it to copy microstructures while retaining also the nano roughness which you offered before. You can have it optically flat. Here on the right, you see a retroreflective pyramid, almost 100 microns high, but still it is optically flat depending on, for example, the structured drum you use. So you really copy it in your UV coating. And that's one of the key steps we use to, together with partners, produce these structured foils. But this is just one step. And there are many steps to come from development to a product. And that's where I want to talk about this presentation a bit with you guys. We try to, at which point the customer comes to us or a project partner, we want to scale up or produce or develop something all the way to the market. That's where we help. We try to cover all these competencies to leverage such scientific knowledge for commercial applications. So from idea to a prototype, from prototype to a product, and from product to manufacturing. And in any of these steps, a lot can go wrong, a lot has to be done. And I want to show you a little bit of what we encountered, what we learned, what we saw by developing a glare control foil for office lighting. Typically, with such a micro-optically structured foil, you control the light of a luminaire, for example, so that it is you don't have any glare beams hitting your person beside of you. or sitting up towards you. So this is what I want to use as an example. And the first step is inspiration or understanding the effect. What do you want to use to solve a customer's problem? Here, the customer's remark was quite easy, quite clear. It had to be an anti-glare foil, and it had to be endless. They didn't want to have any seams. They want to have the possibility to have 1.5 meter lamps. They want to have 5 meter lamps, maybe even want to have 20 meter luminaires length without any optical seams. And it should be microstructured. You do not want to see the microstructure. Glare control or the effect has been known, that it has been sold. Here a very short recap of how that looks like. If you have a flat plate and you have here an LED, you have certain, on a shallow angle, beams of the LED becomes glare beams. But if you then change the angle of the second interface, you can make sure that it doesn't bend to become a glare beam. In very short, that is the essence. If you then understand the effect, you can think of how do I want to put it on a structured drum. The glare control structure needs to be in 3D in the whole room. So it should be 360 degrees. So you are quite quickly thinking about an hexagonally or arranged cone structure. That's where we start. And then you want to make, you want to see how do you get a high performance. Then we or in different kind of projects with partners, if we cannot do it alone, we start to model and simulation step. Here, for example, we try to model really that what the customer needed, the customer wanted, that is the luminous flux here on the left per luminous area for an UGR value below 19. That's the anti-glare norms as used for office lighting. So we really did it, calculated and modeled it exactly as the customer later used it. And then we try to vary the structure, we try to vary the angle and see where is our optimum. So you can directly see where your optimum is. However, this is of course one of the key differentiators for the customer, but it's not all. Your light distribution curve also needs to fit. Does it have to be wide? Does it have to be narrow? The customer always have a preference there. So that's also something we modeled at the same time. And then combining those two, you can pick to make a compromise. How does my light distribution curve needs to look like? And what kind of performance do I want? This is not something we just modeled as a foil and a structure. We also modeled the customer's luminaire. We modeled the material constants in there. We try to put as much in there as we can to immediately come to how a customer in real life would have it, if possible. Now you have made a decision how your structure should look like. The first thing is you want to make it real. You want to make a drum out of it or a mold. As I said before, the customer specification was seamless. That means we luckily do roll to roll, so that is possible, but then you need to have it seamless on a drum. And that limits your tooling options quite a lot. Luckily, we have a few good partners who can do those kind of things. And the requirements were perfection on a seamless imprinting tool, which is harder than you think. If you have these cones here on the left, you have many millions of perfect cones. You don't want to have any variation or damage, and you want to have tool-to-tool repeatability. If I want to buy the second or third tool, it needs to be exactly the same quality because that's what I promised my customer. And if we or a partner cannot do these kind of things, we try to help them to obtain the quality we need. Here on the right, I show you a few of the challenges which were expected because it's not easy, but which we see in between. For example, we saw some tool damage here in between of the drum. We saw some very, very cool structuring mistakes. We saw double tips, we saw line defects, but in the end, we together came to a part where we really had a production quality structured drum without flawless. And then you can really start your development. You have a way to structure it. You have your structure, and then you can start optimizing. As I said, we were trying to optimize the anti-glare performance. And there are several things come together in your product development. Of course, it's just the tooling, the structure. However, here on the left, I show you a baseline picture with a baseline measurement, call it baseline, of the first tool we had and the first replication. Everything fine, looked quite okay what we expected to our first thoughts. Then you start measuring it, and then you start optimizing. So we optimized. We were not always too happy of the replication. We optimized the lacquer and the replication process to have less defects. And that just was more that we expected. And already in this step, we increased the performance, the anti-glare performance with more than 20%. And then we made 2 more iterations where we have a second tool and a third tool and improved the replication even further. And in the end, without changing any designs or something, just developing the product with and understanding the product, we improved the performance from start to end more than 40%. And this was also confirmed by integrated in the customer products. So you now have a proof of concept, which also has a high efficiency. And then I want to go a little bit more in detail in the lacquer, how the lacquer plays into this. As I say, we have here improved the replication. The lacquer is a key differentiator and has interaction throughout the whole development process. It influences the product performance, the optical quality, the product stability in lifetime, the production speed, the process stability, post-processing possibilities. Luckily for us, it's one of our main in-house skills. I have many colleagues who are very good at formulating or developing UV coatings, for example. That's luckily what I have working at BASF Coatings. To show a little bit where that comes into play, here at the bottom, I show you again the process of replication. We have here a foil, we have here a wet UV coating, and you press a structure drum in there. And then at first you like in the sandbox, you just replicate it in there. But there's quite a lot of physics and chemistry in there where the UV coating plays a large role. Of course, the machine also, but the knobs you can turn at the coating. Viscosity plays a very big role here, for example. You can have entrapment of air bubbles or not. If you tune your recipe right, you can also determine how long you can run the drum without having to clean it or without having to throw it away or restructure it, all by just tuning your lacquer. To give a few examples, of course, nothing goes right at the first time. At the beginning, we did not really optimize all these different aspects together. We just had a good coating and a good machine, and we did not optimize them together. And here at the left, you see something I never would have want to show or send to a customer before. You see a nice anti-glare foil, which is totally curled up. Here, customer cannot integrate that in a product. After understanding what we are doing, and it took some time, optimizing these things together, like structure, lacquer, foil, production process, they are very nicely flat-lying. Just a short example of what you can do when you integrate these things. Furthermore, to go a little bit more into detail, what I mean with lifetime, the influence of lacquer on lifetime. Here are a few examples of customer requirements we typically get. For example, here's UV stability of our product is of course influenced in the lacquer you have, or here is on the left side the blue light stability, where the customer wanted to have proof that after a long time use in luminaire, the color of the foil did not change. So that's what we did here. We did more than 100 days of irradiation with a blue LED and show them, look, our B value, so that what comes for yellow, does not change over time that greatly and match the specification of the customer. On the other side, we also have not for this glare control foil, but also for other products, we have also a lot of outdoor stability questions or requirements. And then you're talking about 1000 hours of UVA, UVB stability, temperature cycling with high humidity. Or here at the bottom right, I brought one example. It's a test from the automotive sector. It's called WOMCAM 180, which has a very high UV dose, temperature cycling, it has rain on top, and it has a nice correlation on a car, of course. Every 1000 hours of this test roughly is 3 years of use driving around in Florida. And you can see here what happens if you did not optimize your UV coating. So at the beginning, we start doing this. We had UV coatings which are very nice structurable, but they were not optimized for outside durability, for example. After 500 hours, they were completely yellow, and after 3000 hours, there's not a foil or not a structured foil anymore. Here at the top, you have to believe me, yes, there is a structured foil there. after 3,000 hours, he's still at the left. I cannot see the difference. It has not been yellowed. So there we made really big steps to outdoor weatherability. Then you have a product design. You have a product, you make it small, you make some first roll-to-roll imprints, and you had a nice product. And then you need to continue because you definitely cannot deliver anything at a customer yet. You have to finalize a detailed production concept, consider all the interdependencies. There's always small things which has major impacts. You have to freeze your product design. So really, in every step, determine the process parameters. How does it influence your product quality? And then we go on and produce really a small batch without selling anything, several hundred meters, maybe thousands of meters, and go through all the relevant steps, because always something goes wrong. And we try to come to a point really until the end, until the packaged product which we want to send to a customer. And one of the things I want to show you with, of course, at the beginning, you don't think it can go wrong. We, of course, did small samples and stuff like that, but we had a small problem at the post-processing. Post-processing is, for example, cutting the rolls or patches, laminating adhesive to the foil, etc. And we did some initial tests, everything looked fine. And then you start your scale up. And then you see that a certain amount of the rolls have cutting defects. Of course, you want smooth cutting edges and no scratches. And here you see some scratches, you see some coating defects. And then you talk with your partner. He uses some special equipment like knives and rolls, and then it diminishes the problem, but the problem is still there. And then you need to go back 2-3 steps, really change. For example, here we did change the coating formulation for improved adhesion and cuttability. In the end, really come to a nicely cut foil with no defects over all the rolls we produced. And then you really can start to scale up. You need to scale up to, you want to make tens of kilometers of this stuff. So do you want to, you need to source the materials, source the raw coating materials that you can have. Instead of kilos, 10 kilos, you have 100 kilos or 1,000 kilos. The foil, you want to investigate also the smaller defects which happens in 1 or 2% of the cases. You implement a quality control, especially for this product. This is you're talking about a glare control foil, which of course has special color requirements. So then you, for example, implement extra color measurements for your raw material inspection. And then you integrate it at the customer, which is unique for every customer. And then in the end, you can launch a product, which we did last year. We launched the BSF glare control foil. I talked about the high performance of the foil, which is on par with the premium plates you can buy. Not exactly, the plates are still better, but we are coming close. It has an aesthetically pleasing design, as the customer required. We have small microstructures which you cannot see, so it looks homogeneous. We offer hundreds of meters of this thing, so you can make your luminaires as long as you want, and we can offer long-term durability under harsh conditions. And as a last sheet, I want to give a small outlook what we're working at right now. So envision you have a luminaire, or a customer has a product design which has our anti-glare foil in it. We have the vision that we want to offer our customer the opportunity to just exchange our glare control foil for a different foil and introduce a new functionality. So we're now working on our wall washer functionality. And here on the top right, you see a few of those simulations of the kind of performance we want to aim for by just interchanging the anti-glare foil without changing the luminaire design, for example. Which is roughly brings me to the end of my presentation. I want to thank you for your attention. Thanks for the team. If you want to have any more information, you can go to our website, email us. It's a Lightning Solutions email, but if you have more questions or proposals, or you want to talk with us about other projects than optics, you can also use this email address. Thank you.
Thank you very much, Sven. for this impressive and nice presentation. Are there any questions? There's a short feedback which I would like to share with you in the chat. Fantastic, the presentation of BASF. So I would like to. Oh yeah.
Thank you, Ruth.
I would have one question with respect to the long-time stability for outdoor application. If we think of solar, so PV applications, so the environment is even harsher and it is even more hard to have the long-term stability if it is really meant to stay in the sun for 20 years. What is the UV lacquer reacting, or how is the UV lacquer reacting? Can you make it stable for 20 years in the sun?
Yes. Well, that was maybe too quickly. I did not put any UV lacquer 20 years in the sun yet. So I cannot say yes to that. But there are, in the PV, for example, there are accelerated weathering tests which would indicate that you have these kinds of stability. Those was in a previous presentation also shared as the DAMP test, for example, 85 degrees, 85% humidity. And that's one of the tests we also do with our lacquers. And there we have lacquers which withstand 2,000, 3,000 hours of these tests, which is normally for the PV market, that direction which you want to go. That doesn't mean if you have a UV lacquer that survives that, that does not mean you have a product that survives that, because the whole product needs to survive that. So that's also what we try to offer here, which I want to envision with my presentation. We do not only make or develop a lacquer, we try to really make a product out of it, which we then produce.
Okay, so but when it is in the sun for such a long period of time, do you see the optical effects like yellowing and index more critical, or is there also a problem with the adhesion between substrate and the lacquer?
That's hard to say definitive without knowing exactly the buildup which you are using. But if I have to guess, I would say adhesion. Because it depends on the foil you're using. There are, for example, traffic signs out there which also need to withstand 20, 30 years. There are polymers in there, but it really depends on which polymer you're using. If I may, an easy example, and I don't want to make any bad impressions, but there's a big difference between outside weatherability between polycarbonate and PMMA, for example. Polycarbonate is a better optic material. PMMA is better for weatherability, for example, from my amateur standpoint. It's just a general thing. So that really depends on a coating can withstand it, but what is more in your product? Do you have adhesives in there? Do you have a metal coating in there? Do you have, which foils do you have in there, which will limit your lifetime?
Mm-hmm. One last question, because you mentioned PET, PMMA, PC, especially when it comes to UV lacquers on such substrates, we find good solutions on PET and PC, but few for PMMA. Is there a chemical reason for that?
Yes. If you have a formulation, normally you put ingredients in there who attack the surface. If I may, to make it very general and quick, we can talk offline more if you want. And for PET or PC, it's easier to attack the surface or to break certain bonds and to make reactive species than on PMMA. Maybe the real chemist in the audience can explain that much better than me.
No, but it's good. I'm a mechanical engineer, so this is this is enough. Okay, thank you, Sven, for this nice presentation, this nice insight into the development of new products based on films. So we come to the last presentation for today, which is presented by Mrs. Pfingstgraf. She obtained her master degree in optical technology and image processing in 2019. Since May 2019, she works as optical engineer first for Evonik, now after the transition into Röhm for Röhm GmbH. Today, Mrs. Pfingstgraf will give us an insight into characterization and simulation methods for materials with volume scattering elements. I understood that you will do this jointly with Mr. Schmidt. I'm not sure if this is right. Yes, it seems to be right. So Arne Schmidt will also bring into this round his experience. He's plastic and mechanical engineer and started his career at Röhm, respectively Degussa, Evonik in 2006. And he's head of the technical marketing automotive for Röhm today. So looking forward to your presentation.
Need to unmute. Thank you for your introduction. Now I have presenter rights and I hope you can see my screen.
Not yet.
Yes, I can see
yes.
it.
Yes?
Ah, yes, perfect.
That's perfect. Okay, thanks for the opportunity to present our latest results on the optical simulation of diffuse polymers. And for sure, as a raw material producer of PMMA with a brand name Plexiglass, we have done our research on our product, but all the slides and all the technologies you can see and routes to a valid simulation model we will present can be applied to each other optical polymer as well. So on today, I'm happy. I'm just a mechanical engineer and I have limited knowledge about simulation. And I have our simulation expert on board, Mrs. Pfingstgraf, and she will take over at the middle of the presentation. Some words about our agenda, the motivation, the basics of light scattering, composition of volume scattering, so what we are doing in our plants, measuring and physical fitting of diffuse properties, and finally the optical simulation. Yeah, we have heard a lot about structures and micro and nano structures to manage the light source. We are giving the opportunity to select a little bit different directions, so to avoid structures on our plastics parts, to create light management by using diffuse or volume scattering materials. So the LED is everywhere, the light bulb disappears, for sure. Efficiency is much better, but the LED is a point light source with a high brightness and especially high power LEDs. If you watch into them directly, they can harm human eyes. So the high brightness, the high light source must be managed, and you can use structured plastics or diffuse plastics. So on the left side, you can see some milky plastic parts, and here the diffusive power of the upper plastic part is not sufficient enough. So I take the laser pointer, and if you increase the scattering power of the plastic part, you get a homogeneous illumination. This is a very simple system. If we aim now for a little bit more complex system, so this is now a 3D shaped diffusive part in the taillight of a car, for example, and it has to follow very strict regulations in regards to color, in regards to luminous angle. So what can happen if you are working with diffuse plastics in the engineering phase, which is quite new up to now? Transparent plastics are in that industry known for 60, 70 years, and diffuse plastics roughly 5 to 8 years. If you do the engineering wrong, you can get color change, for example, because volume scattering is a function of the wavelengths of the incoming light. If you use a too low scattering material, you can get insufficient light scattering, so you can glare the traffic behind you. And if you try to avoid that one, you can use very high scattering power plastic. You will get excessive light scattering, but you will lose light and the efficiency of your system goes dramatically down. So some basics about light scattering. So at first, we have no scattering, very simple. We have on the figure number 1, we have a ray of light hits a material, gets changed in its direction by Fresnel laws, but inside the material, no change in the direction. In figure 2, we have the single scattering event. So our light beam hits one particle and is scattered, something in that function, and leaves and changes its direction and leaves the material. If we multiply the single scattering event, we are coming to multiple scattering. And this is something we want to have in real applications. So if we look a little bit deeper into the single scattering event, we have a plastic part or an anorganic part, which has a defined size. Here it's a bead or a defined shape with a diameter. And we have a chemical composition which will determine a refractive index, and this refractive index must be different to the matrix of the matrix polymer. And if a light beam hits the material, we can detect the angular scattering distribution. This is mostly a mathematical function, or can be fitted to mathematical function. This is the single scattering event. If we go to the multiple scattering, we have to consider an additional parameter. It's the mean free path. It's the mean distance between two particles that the light can travel without interact with a particle. So this is the concentration factor. So if we go take a look at different particles, there are inorganic particles, there are organic particles. Just if we distinguish in size of these particles, we have to take a look at Rayleigh scattering. Here, the particle size is much, much longer than the wavelengths of the incoming light. Rayleigh scattering shows very strong scattering forward and backward. So there is no preferred direction of the light, and it's strongly dependent on wavelengths. This happens in gases or atmosphere, humidity in the air. This is Rayleigh scattering. For plastics are more interesting the Mie scattering and the geometrical optics. Mie scattering means the particle size is roughly in the same size of the wavelengths or a little bit above. So Mie scattering shows a strong forward scattering, but as well 20 to 30% backward scattering, reflective scattering. In a lot of real life application, this light is lost. So if we go forward to geometrical optics, we increase again the particle size. It must be much, much bigger than the size of the wavelengths of the incoming light. Forward scattering shows a lower scattering power. So as you can see here, but you minimize the reflective scattering. It's an advantage, more efficient, but in regards to energy efficiency, but the scattering power is lower. What are we doing to compose our diffuse materials? Best way is to use clear plastic matrix polymer, no color, no light scattering. And then you introduce by a compounder, twin screw compounder is preferred, particles. These are real pictures of particles. You can introduce large particles or rather small particles, and then you get something like that. This is the matrix, and here you can see incorporated particles. Our satinized DF products containing the large geometrical scattering particles and the LED range containing these small particles. And that's what we are doing, and our customer is taking the pellets and molding it to diffusive parts. Problem is, before molding comes the engineering, and this is for the moment or up to now sometimes a little bit difficult because the material models available in the simulation systems are often not very precise. So you have to mold, you have to check by milling prototypes and then change the mold and. So the engineering, the development of the application takes longer than it's for just transparent clear plastics. So now I want to hand over to Natalie.
Yes, thank you, Anne, and thank you, Mr. Baum, for the introduction. I hope everything will work fluently because we have some technical problems before, but we will see. So now I will give you some information about our measurement topics and the physical fitting of diffuse properties. How can we measure our scattered material? In our lab, we use a goniometer to measure our plates, and we need an incoming light beam that starts here from the left, and it's orthogonal to our sample. And if the detector is across from the light beam, you measure the scattering angle at 0 degrees. And then the detector moves around the sample and detect the scattered light at each position. You can measure the forward scattering from -90 to 90 degree, and as well the backward scattering if the measurement device can do this. The detector can be a photometer, a radiometer, or a spectroradiometer. The spectroradiometer is able to measure the spectral signal of the scattered light, and this is what we use in our lab. That's what you see here on the right bottom. This is our measurement device, and we are able to measure the forward and backward scattering. Next. Here you see the results of a measurement of our product, plexiglass ADAN LED 0V206 at 3 millimeters. On the left, you see the spectral signal in the visible range. First, the forward scattering from -90 to 90 degree, and the signal is defined in wavelength packages because the dependency on wavelengths for each wavelength is not so high. And in these packages, you can see the dependence better. And you see that the red light has lower scattering properties. At 0 degree, you have a part of unscattered light that goes through the sample without any scattering effect. And with a lower wavelength, the scattering properties gets higher. And the reason for the lower level of the violet curve is our UV absorber in our material, because the wavelength packages is at the limit of the visible range. On the left and right side of the diagram, you see the backward scattering. It's lower as the forward scattering. So as Arne told a few slides ago, this product is in the scattering range. On the right side, we have the diagram to define the half value angle. It's a scattering property of our material. This curve is the sum over all wavelengths weighted with the standard illuminant A and the luminosity function. And the half value angle is defined at the half of the maximum transmittance. So for this product, we have a half value angle around about 40 degrees. So now remember these pictures because you will see them later again with our simulation results. Now I go over to our optical simulation topics. Before I explain how we get the parameters for the simulation model, I give you a short introduction into the simulation process. You need a few input parameters. At first, the phase function of a single scattering particle. It's the internal angular scattering distribution of the single particle. Then you need the concentration of particles. So you can use the mean free path value. and other data as the refractive index or the absorption coefficient. This data is what you can get out of our production information. And if you want to simulate the geometry, you need this data as well. Then you enter all this data in your optical simulation software, and this will calculate multiple scattering from your single scattering data. And the output will be the scattering properties of the optical component. And if you change the structure of your particle or the concentration, the scattering properties will change as well. So if you decrease the concentration, you have a lower scattering properties in your product. There are two ways to evaluate the physical data for the optical simulation. On the left side, you have the scientific approach. You have to start with the evaluation of your matrix polymer. So you need the absorption and the refractive index. And then you analyze the single scattering particle. So you need detailed information of the single particle. And then you evaluate the concentration of particles in your product. So you need the mean free path. If you have all this information, you can create a material model for the simulation and compare this with the results, measured results of your polymer product. If the results are good, you have a validated simulation model. And if not, you have to start from the beginning and do all the steps again. On the other side, you have the experimental approach. You also start with the evaluation of your matrix polymer, but then you use a real-life diffuse polymer product. If you have this product, you need the information of your single scattering. So you have to isolate the single scattering event by a dilution series, or you use very thin samples. If you have this data, you use a mathematical scattering distribution function to fit this to your measured phase function of your single scattering. And the last two steps are the same as in the scientific approach. You create a material model for simulation and compare this results with your measurement. And again, if you have a validated simulation model, you can use this. If not, you have to start from the beginning. We use the experimental approach because for us, there are more advantages, as you can see on the next slide. Here is the scientific approach. The only notable optical data, only notable advantage of the scientific approach is the optical data, because that's very easy to get. Everyone can measure the refractive index or the transmission or what you need. The disadvantage of this scientific approach is the analyze of the single particle. The particle is only one part of the whole process. So here we pay no attention of the other parts of production. And we use industrial products, industrial particles, so they can show tolerances in the refractive index, the radius, or the concentration. And another disadvantage of this approach is that we can have distortion or depolymerization of the particles during the process, and that's nearly impossible to handle these effects in the calculation. On the other side, we have the advantage and disadvantage of the experimental approach. The advantage, of course, is also the knowledge of the optical data. And now we use a real-life product. So this product regards the processing and manufacturing effects. If there is distortion or depolymerization, we will have this in our real sample. We regard this. And because we can dilute our concentration of single scattering particles, we can measure the single scattering. And everyone who has a goniometer or a injection molding machine and know the matrix material without the scattering particles can do this experimental approach as well. The disadvantage of this approach is that you need a high number of measurements because you have to be sure to measure the single scattering. So how can we get the single scattering data? To determine the single scattering on the experimental way, we need special samples with very low concentration. So our standard products have higher concentration of scattering particles. So the multiple scattering is the main effect, and it's not usable for this approach. So we have to decrease the concentration of scattering particles and determine the mean free path for each sample. And depending on the sample thickness, we introduce a new parameter. It's the K factor. The K factor is the ratio of the mean free path and the sample thickness. And he says the higher the K factor, the higher the probability of single scattering. So on the right, you see a diagram of our dilution series. We start with the real product in the left top. You have a high concentration, so you have a low mean free path and a low K factor, and you decrease your concentration of your sample of your scattering particles again and again. And then you go from the multiple scattering range into the single scattering range, where the probability of single scattering gets higher. And if you have a very low concentration, you have a high K factor, and that's what you need to measure the single scattering. And on the next slide, here you see 3 measurements of our dilution series. On the left, you have a real product with a low K factor, so you have a high concentration, and you see the multiple scattering of the product. And around 0 degree, you have another effect. It's the unscattered light of the light source of our gonimeter. So here, photons goes through the sample without any scattering. And now we have to decrease the concentration of scattering particles and go to the diagram in the middle. Here is the question, do we have multiple scattering or is it single scattering? So as Anna said before, the Mies scattering is dependent on wavelengths. So the wavelengths should be separated. And in this diagram, they are mixed, as all in the flanks. So we can say that we have multiple scattering as well, and we have to decrease the concentration again to have a higher K factor and to separate the wavelengths overall measurement part. So in this case, all wavelengths are separated and you see them, and we can say that this is our scattering, a single scattering event. And if you would decrease the concentration again and again, the diagram wouldn't change. So we can say that we use this data for our simulation model, and that we fit the mathematical phase functions to this function. So what kind of phase functions can we use? There's the Henry-Greenstein phase function. You see the formula there. You have only one variable anisotropy factor. And the second function you can use is the Gegenbauer function with 2 variable parameters. And on the right, you see the parameters which we calculated after the mathematical fit to our measured data for 3 wavelengths. And on the next slide, you see the fits for the 3 wavelengths at 450, 550, and 650 nanometers. The measured data is the colored line. And now all measured data are normalized to 1. And on the left, you see the Henry-Greenstein phase function. And hopefully you can see it on the right. The dots is the Gegenbauer phase function. And you see that the results of the Gegenbauer function in all wavelengths is better against the Henny-Greenstein phase function, especially in the flanks, where the scattering information is important. Yes, so for our simulation, we use the Gegenbauer function, and I will show you an example of our simulation that you can see here. On the top, you have a cutoff of our product information of our LED series. And here we have again the example from the beginning, 8N0V206 for 3 millimeters. And you can put this parameters into the input mask of your simulation software. We used LucidShape from Synopsys. And you can see that you're able to you enter the Gegenbauer parameters and you get the results in the diagrams. So plexiglass 8N LED 0V206 at 1 nanometer shows the unscattered light at 0 degrees. So you have a hotspot if you use this product with your light source. That's nothing what you want to have. So you decrease the thickness or the concentration. We increase the thickness of the plate to 3 millimeters and simulate the product again. And you see that we can simulate both thicknesses at the wavelengths. And now you can see as well that we don't have a hotspot anymore. Yes. Last but not least, a short summary and the few bullet points. So at first, the key to optical simulation using light scattering plastics is the phase function of a single particle. So if you have a K factor, a high K factor, the probability of single scattering is higher. The experimental determination of this function offers advantages because it is based on a real-life plastic product. Standards for that procedure are still missing, but we are working on this issue at the VDI VDE 5596 series of standards. The Gegenbauer function shows better results compared to the Henny-Greenstein. And last but not least, the optical simulation for higher systems temperatures are possible for transparent plastics. For the moment, it's not possible for diffuse plastics. So thank you for your attention, and now we're open for questions.
Well, thank you very much. I think this was very good to see that there are good approaches for simulating the scattering effects of those volume scatterers. Are there any questions? I would have two. Well, first, to me, it was the wavelength dependency, which we've seen for this volume scatterers, has been surprisingly high. So there must be a relatively high color shift with this material, even with 3 millimeter. Is this right at the first, in the first, or as first part of the question? And secondly, is there any measure to decrease the wavelength dependency, or well, and at the same time lower the color shift?
Oh, this is a trade-off. Wavelength dependency and scattering power are a trade-off. You cannot combine high scattering power together with low wavelength dependency. Unfortunately, this is physics and it is not possible. You can detect it, for example, if you use diffuse material, have a LED light source behind and project the picture on a white wall, you will detect by visual inspection, you can detect the different colors of the light. Depends a little bit on how strong the scattering is and which scattering regime is used, but it is possible to detect, especially in the area, in the let's say dark and bright areas in this interface area, you can often see color effects.
Mm-hmm.
You can work with structures. You can overlay this full system with structures and try to diffuse a little bit by using structures this this effect, but in general it's physics and you cannot avoid it completely.
Okay. And one more question. Well, we've seen that there are models which work pretty well for the simulation, but well, getting the input parameters is quite complex. Do you support your customers? So if I go into the development of a new product, can we get support from your side when we will look for simulation models?
Yeah, that's the reason why we pay Natalie's salary here at Röhm. For sure, our target is to empower our customers to be much faster in the engineering and development phase of products. So we are releasing step by step valid simulation models. Our target is always a wavelength dependent simulation model. And often you find in the software systems simulations models that are not wavelengths dependent, and in according to our experience, you need a wavelength dependency. If you're working with red light, it's something different when working with a conversion LED. But we will release in the next months more and more simulation models, and we will implement them for sure in the standard systems.
Good.
I have an additional question. When we try to use this material in praxis, we realize that the scattering performances are dependent on molding parameters, on plasticizing and melt flow during molding. Do you have experience with effects like that?
Yes, that's the reason. So why we use the experimental approach. So we are using plastic particles, high cross-link plastics particles as scattering particles.
Mm-hmm.
And for sure, plastics can be destroyed by super high heat or high shear rates, and they can show distortion. So they are getting soft rubber-like during the injection molding. And if you freeze the part very fast, you can get anisotropic scattering properties. So this can happen.
Mm-hmm.
One thing to avoid it is we are using for our simulation parameters the experimental approach to consider depolymerization effects of the material, and for sure distortion effects. We are checking our materials according to the tendency to distortion effects. We call it particle distortion. But yes, the design, the engineering design and mold flow design should be cross-checked with the optical simulation. So breakthroughs, weld lines, and such kind of things should be avoided, because this will create anisotropic scattering in that weld line area and will look horrible at the parts. Some people like it, but mostly you should not have such kind of things.
And can you give tolerances to these scattering models? If it comes to lot variations, are there any tolerances which you can specify?
Yeah, this is now a topic for our quality management. So our half value angle is, so we adjust our products according to half value angle. Each lot we measure the half value angle. So this means 1 point on this parabolic shape is detected in our production, and we adjust our products according to that. But as Natalie mentioned, we are working with industrial particles. These are not rocket science particles. They can show fluctuation and they can show tolerances. In general, for the most lighting situations, I'm talking for automotive now, the tolerance we can offer are good and satisfying for the industry. But we have tighter tolerances for, let's say, very special application.
Many thanks.
Okay, any additional question? Then thank you again for this very good presentation. And yeah, then we can close the presentation session for this afternoon. So, but I would like you for one more favor. It would be very nice. Normally we take group photos if we are in a presence or in a normal conference. This is of course not possible here, but if you're open for being on LinkedIn, I would ask you to switch on your camera right now. We will make a screenshot and maybe use this also for LinkedIn. So if you're willing to do this, I would be very happy. And then we have also a little bit of an impression who has been in the call. Very nice. Great. Very good. Okay, Helen, you're hardly in the middle of the picture of the screen, but you must take the screenshot now. Great. Oh, this looks good. Very nice. Okay, well then I have one more favor. So before you leave the call, I would like to ask you to help us enhancing our events by giving us a feedback in our evaluation form. Helen already linked or has posted the link in the call. It would be very nice if you it takes just 1 minute if you take the time for filling out this this form which we prepared. So well, and now I would like to thank the audience and of course all the presenters for this impressive presentations and the organizers of the day. Special thank goes out to Jose and the EPIC team. I think this was very good to have you here. And well, I pretty much looking forward to seeing you in one of our next virtual meetings, or even better, as soon as possible in person. We all hope that this will be possible soon in the near future. Jose, if you want, you can give the closing remarks for this event.
Thank you so much for a great afternoon. I love you all. Take good care of each other, wash your hands and wear a mask. Stay safe. Soon we're gonna be traveling again. Take care. Bye-bye.
Thank you. Goodbye, everyone.
Bye, guys.
I really want to travel again. I want to hug Ruth. I want to hug Ruth. If I don't finish a meeting hugging Ruth, it's weird. I want to have dinner with all of you tonight. Let's all go for dinner in Aachen.
Yeah, well, Aachen.
Next time again. Great. Goodbye.
Bye. Bye-bye.
Goodbye.
Bye-bye. Thank you.
Have a nice evening.
Bye.
Amazing presentation, Gabri. Really, really incredible.
Thank you, Jose. Bye-bye.
Bye, Jose.
Bye. Take care. Good to see you again.
Bye.
Mark, you were really good today. And I think there's lots of opportunities there for collaboration. Really, really good.
Thank you. Thank you. Have a nice evening.
You too. Bye-bye.
Bye. Thank you.
Ja, ich habe dann
Gut gemacht, Helen.